Welcome everyone, and thank you all for joining us here in the session on the data distribution system. TX1, Trend Micro, and AD-Link are presenting this project together, but we're indebted to ADS Robotics, who also took part in this research. I'll first give a very shallow introduction to DDS, because it's not that well known in the world, then hand over to Federico and Ta-Lun for presenting the substance of the research. And there are many software-based control systems in the world that hook up sensors and actuators to control and monitoring application. Often, these systems are used to quite critical applications, such as your vacuum robot or a power plant or a robot for milking cows or a traffic control. And DDS really was invented for such systems, taking the need for distribution, longevity, and fault tolerance as a starting point. It is optimized for peer-to-peer systems, and many implementations have no brokers, use multicast for discovery and for data, and allow you to in small systems allow you to run everything without any need for configuration. To the application, it is often just a library. Sometimes there are some accompanying executables. It handles the communication with the other parts in the system. Interoperability between different implementations, platforms, and programming languages is a core principle. The key to that interoperability, and indeed many of the other entities, is that it handles typed data. The data types are declared using an interface definition language that is quite similar to C or protobuf, and it features all the usual suspects, like integers, floating points, strings, enumerated types, records, you name it. Relatively recently, features for the type evolution got added. Before one would evolve a system by adding new types, now one can also choose to evolve the existing types. Altogether, the types can grow as complex as you need them to be. But there is more to it than just types. There are also many different quality of service settings to control how exactly the data is handled and how it is protected. This coverage covers such things as reliability, automatic handling of historical data by the middleware, encryption, deadlines, liveness monitoring, etc., etc. These are all specified in a reasonably uniform way, either programmatically or often through XML files. The programmer doesn't see much of this. Once the types have been defined and preprocessed, all that really needs to be done is creating a few objects, and you can start communicating with the other processes in the network. The experience is that of a databus. And actually, it is old enough to have a fair claim to being the first software databus in the world. The first description of DDS, the DDS model, is by my father in a document dated the 29th of February 1984. So at first sight, DDS looks very much like MQTT or any other PubSub protocol, but because there are also topics, publishers, subscribers, etc. But there are some key differences. And one is that it is focused on, nowadays, is called edge computing. The other is that it has more knowledge of the data type, the data content, than most of the other systems, and that this additional knowledge allows you to do query evaluation or filtering in middleware, and also to let the middleware take over some of the responsibility for maintaining the data set. And so you can even configure it to act like a simple distributed replicated relational database. It's also standard, maintained by the OMG, the Object Management Group, which you've probably heard of because of UML. If you're old enough, they're also the organization that standardized Corba. I think they were founded for that. Various of the DDS implementers are OMG members and actively develop both the specification and implementations. While each implementation has its own unique features, when multiple implementers end up doing the same thing, they do tend to get together and extend the specification. And also important to notice that some of these are completely open source and some of them are closed source, and then there is some in-between stuff. Okay. Now, I've mentioned a few, or alluded to some areas where DDS is used, but I think it is important in this context to make it a little bit more explicit, to give you a really good appreciation of why DDS-based systems are critical in the world. The first example is transportation. ProRail is the Dutch national railway infrastructure where the track control system, switches, semaphores, reserving the right-of-way for trains, things like that, completely relies on DDS for communication across the system. CoFlight is a new European air traffic management system. DDS is used, for example, for distributing flight plan updates throughout the system. And NAV Canada is similar. And in transportation, there are, of course, also autonomous vehicles, which are stuffed with sensors and real-time sharing and processing of this data is at the core of the system. These feature quite smallish networks of quite powerful ECUs, and there are quite a few where DDS is used to integrate these. In many cases, these autonomous vehicles aren't directly written using DDS. They use what is called ROS2, the robot operating system, but that itself is based on DDS. I also see ROS2 is in industrial robotics. There is a whole group affiliated with the ROS2 movement development world called ROS Industrial, which is focused on support of ROS in industrial robotics, and so also DDS. Furthermore, there is space. There's not just aviation, also space. And for example, the Kennedy Space Center monitors hundreds of thousands of parameters during launches. But that's just on land mostly, but DDS also really travels into space. For example, RTI was used in the first launch of the Orion spacecraft. And finally, as a final example, there's healthcare, obviously important. There are many other examples I could give, but I think that this suffices to make it really clear why DDS has become critical to our world. And with that, I'd like to give the floor to Federico.
Thank you, Erik. I would say you did a very good job convincing us that DDS is a critical protocol. So any findings, any security findings is going to be impactful and important for any of the downstream vendors that adopt it as a networking layer. DDS is quite complex. You see here from the packet definition that it has several extensions on the side, which are there mostly for making it future-proof, because, for example, it has to make room for extensible types. There is the interface definition language that Erik told you about briefly. There is a DDS security extension, and so on. So we decided to start from the foundation layer of the whole DDS ecosystem, which is called RTPS, not to be confused with RTSP, which is the popular streaming protocol. RTPS stands for real-time publish subscribe protocols and tells you immediately what the nature of the protocol is. The frame starts with a magic number that is the actual protocol name. So the 4 letters RTPS. Then there is the protocol version, and then there is the vendor ID. There are several vendors that are officially supported, which are the OMG members. On any other vendors, for example, if you want to create your own implementation, you will be identified as an unknown vendor unless you receive certification from OMG. Then there is a globally unique identifier, just a prefix here, that identifies that helps the receiver determine if the packet has to be accepted or not, because maybe it's for another participant. Then what comes next is essentially a list of submessages. Each submessage has an ID, which is actually its type, we'll see later. Then there is a 1 byte of flags, and then there is a length field, which is called octet to next header. I highlighted it because normally when you do vulnerability research on a network protocol, you start to pinpoint the length fields, which is normally where you can find overflows and these kind of bugs, and tells essentially what the size of the reminder packet is. The submessage ID can take any of these enumeration values. This is taken straight from the specifications, error included, but we decided to leave it there and not report it as a vulnerability because fortunately no compilers will accept this value, probably not even a syntax highlighter. Essentially we have a variety of messages. For example, you can have a message that informs the other participant about the time. It's a timestamp message, informational message. And then, for example, there is the data message, which is possibly the most interesting one because it's where the encapsulation of the upper layer protocols happens. So is essentially where DDS lives. You notice that in a data packet, there is the flag that is set to data present, which helps the parsing to understand that there is data coming. And the actually serialized data is encoded into the same format that is used in Corba. So this is the second time that we say Corba in this presentation. We are definitely nostalgics. The common data representation can be in little endian or big endian, depending on the implementation choices. So looking at all of this, it seems like natural to implement a dissector. There is a dissector in Wireshark already, but we wanted something more scriptable. So I started to look into Scapy, and I noticed that there was no RTPS layer, so I decided to create one. And then with the help of Alias Robotics, which is also in this project, we increased the dissection capabilities of the Scapy layer, even though it turned out quite painful, because I mentioned quickly about the endianess. Well, I figured out after reading the specs closely that the endianess of each submessage is independent from the endianess of the other messages. And some of the fields follow that endianess, and some other fields are always little endian or always big endian. It's really, really complex to keep track of all of this. We cannot simply have a global endianess bit set at the global class, for example. We have to keep track of the endianess for each of the packets. So in the list of packets that compose an RTPS message, dispatched by their type, as I told you at the beginning, for example, the data types will pull out the RTPS submessage data class, which includes the data packet, which follows the endianess for decoding and so on. So here, instead of using the default packet field class, I created a subclass. It's called ePacket field, which automatically sets the endianess according to the flags and propagates the endianess to any of the subclass, and so on and so on. So if you're interested in using it, here is the pull request that hopefully by the end of this presentation, when this presentation will go live, it will be integrated. We are working with Scapy developers to make some tests pass, but it's functional. So if you can use it, even if it's not included into Scapy yet, you can use the fork that I provided and use it right away. Great. So now that we have a good understanding of how DDS work and how RTPS packets look like, it's time to start to look for vulnerabilities. And yes, we did try, and we could go on using a network-based approach, but given that we have some of the open source implementations out there, we decided to do some application fuzzing as well. So here I want to give the floor to Ta-Lun.
So thank you, Federico. Ta-Lun here. Now that we had a network fuzzer and know the protocol pretty well, we might want to start fuzzing. But before investing time and resources in running a full-blown fuzzing campaign, you might want to go the cheap way to see if we're lucky, right? So we gave it a shot and started to fumble with some of the fields. In our case, we find one of our biggest findings by fumbling with this field. And it turned out that we have some quite luck. That reminds me of a joke. Sometimes while doing reverse engineering using strings and VIN, you would find the things you wanted more quicker than IDA-Pro. And in this case, we broke the spec. So what we did basically is we copy the RTPS payload from Wireshark and paste it into Python and using pound tools to set them. Then we randomly fumble with some of the fields, like changing ID to non-existing IDs, maybe changing length and port to either very large or very small values or even zeros. And what we did is we changed IP to some random addresses. In our testing, we use Google DNS to do this because it's very simple to type. But it's a very bad thing to do. Sorry, Google. But in our testing, if we change IPs to some random IPs, in our case, it's Google, we'll see our tested implementations will start to send out packets like crazy. we're kind of confused, but it's apparently that we have found some kind of reflection or amplification attack. And this attack works on all implementations. So at this point, we believe we have somehow broken the DDS spec. And by looking further into the spec, it allows one to write arbitrary IPs into the field, and there's no any sanity checks or whitelisting implemented. And there are some implementations that result in less efficient amplifiers. Maybe that's because they're on the cautious side. And we understand that some of the implementations are not even interested in this. It makes sense because you have to actually broke the spec in order to be not affected by this attack. And here you can see the demo of our RTPS network reflection. And back to the slides. After we found this, we're kind of struggle on how do we disclose this because it's too big for us. However, at the end of the day, we found out that it's not an implementation vulnerability because it affects all the implementation. Thus, it's a bug in the specs because the auto-discovery protocol has to send out these packets. However, we still believe that it's something to be taken care of in the next revision of the standard. So we have submitted it to the OMG. We waited for canonical 120 days after we submitted it to the implementations before talking about this at Black Hat. Also, as a last resort, we also reach out to US ICS CERT for advice. Anyway, on this page, you can see a comparative sheet of how implementations work against our attack. You can see some implementations, they're immune to this attack in the first place because they have implement some kind of exponential backoff. And some of the implementations, they have patched it in most recent release. And for some implementations, however, they're not interested in patching it. So we should get on to white box application fuzzing. If you're using any other open source implementation of DDS, or you have paid enough money to your vendor, then they might give you the source code so you can do fuzzing on the source code. But usually while dealing with frameworks with this size, you wouldn't even know how to start. So we have a masterpiece here on this page to show you how to think outside the box. So take an example, when one participant wants to send a data over network to another participant in DDS, it will send it and the recipient will do some receiving function, and then you'll try to do something. And then it will go to the actual deserialized section. After that, it will try to parse the results and pack the results into a data packet and then send it back to the original participant. And so the general idea while doing fuzzing is that you only want to fuzz what is necessary. Otherwise, you might end up with lots of garbage information. And how to find the deserialized thing? You can look into the code for a valid preamble, such as for letters RTPS. You can look for where it's trying to parse headers, such as GUID prefix or version. You can look for error messages in strings. You can look for something like deserialized fail, because that's some implementations will show on the screen while you're sending it an embedded packet. And you can also try to look for a very big switch case, because in some implementations, it would use that to determine which handlers to go for corresponding PIDs. Anyway, let's go to a quick overview of good fuzzing targets. Well, you can maybe try to run your implementations and hook it up with GDB and do a backtrace and see which function which has a name of serializer or deserializer, or simply look for that in the source code. The reason that we focus on deserializer and serializer in our research is because we believe humanity cannot build a rugged and secure deserializer. As you can see, like for languages like Java and PHP, they're having problems with serialization all the time. And we're still seeing people misusing Pickle from Python. So why not hit the deserializer? And from here, you can see how to find the corresponding handlers in some of the implementations. And here's another one. Here it is trying to parse through different PIDs and try to handle data. And here you can see it's looking for 4 letters, RTPS, and go on to further processing. Anyways, you would end up with a fuzzing harness like this. It's not a very good harness because it actually would generate some false positives. But you get the idea, and we did find 2 vulnerabilities based on this harness. For example, the one here, this is generated by our fuzzer. This is indeed a slow low-risk attack. Why it is slow low-risk is because it has something to do with internal processes of DDS. Anyways, here's a complete sheet of what we found via fuzzing. And in some cases, you wouldn't even have the source code. So what would it do? Well, it is not a problem to us. You can throw it into the compiler and debug to find good fuzzing targets. But be aware that some of the implementations, they have some kind of end-user license agreement that you have to be wary of. And if you want to do fuzzing, well, AFL supports cumulative binary instrumentations. So maybe you can use that, but we didn't because we found out that there's a wonderful project called afl-unicom. It uses Unicom engine under the hood. So what it does is that you want to dump the context of GDB in the first place and throw it into afl-unicom. It will restore the context on every iteration. It will set register and memories, and it will set RIP, then start execution. And after it started execution, you want to insert your fuzzing payload and see if it crashes. However, there are some challenges. One is very obvious that you must locate the correct function. And you have to also re-implement some memory operation functions because in afl-unicom, it doesn't load external libraries. That makes sense. So you have to maybe rewrite malloc and memset and implement it in Python. And because afl-unicom supports Python, so we use Python for our fuzzing harness, and the speed is not very great. And it's also due to how afl-unicom works. So here you can see it's running very slow. However, we have came up with the idea to solve a problem, which is we shamelessly throw money to the problem. Well, we found out that by using AMD machines on Amazon Cloud, it somehow runs like 2 times faster than Intel machines. This is the biggest one that one can use on Amazon Cloud without request for capacity increases. And we think it's affordable by various means, especially time, because we don't have to rewrite harness in C and to optimize afl-unicom on how context is restored. But be wary of some gimmicks with CLAN on AMD servers, because it has something to do with speculative execution, and some instruction will be compiled into embedded ones. So, as you can see, here's a graph of what we have found with binary fuzzing. And let's get back to Federico.
Thank you very much, Ta-Lun. Let's now look into the configurability of DDS. We said at the beginning that with an XML file, one could specify an entire DDS system, including quality of service, security settings, and so on. So parsing XML files is something that covers an important role for DDS implementations. We found three broad cases. One is those vendors that decided to use well-tested XML library, which is a good practice. The OK way, which is vendors that decided to re-implement XML parsing, which can be actually quite good if it's paired with continuous testing. So we found cases where the implementation was almost free from bugs, comparable to the first case, and the bad way, which unfortunately we have found only one case of a vendor that was using an XML library that is no longer maintained for more than a decade. And while I was working on this, without revealing the name of the vendor, I tweeted because I was a bit frustrated to find this in 2021, and I figured I wasn't the only one having found that library. The library is called Easy XML, which is a port of XML's library of PHP into C, right? And it seems that many routers' firmwares are based on the same library, according to what Richard Johnson has found. And we also have found this DDS vendor that I will reveal the name in a few slides, that uses this library from 2006, which is unmaintained. Even the mailing list is dead. And the latest version was 0.8.5, and this vendor has renamed it into 1.0.0, leaving everything else of the code untouched, including bugs, of course. For other vendors, it was enough to use Radamsa plus some scripting, and that allowed us to find three interesting cases in RTI. One case could allow the attacker to partially override the instruction pointer, which is good. And another case allows partial control of the stack up to the environment variables. Here is a table with the updated cases. I highlight and reveal now the name of that vendor that used the unmaintained library, which happens to be the vendor that we haven't been able to talk to. It's the only one that has never responded to more than 5 attempts to contact them through the vulnerability brokers such as ZDI, through the Korean CERT, and through 2 personal emails that we send to the support. They don't have a security contact. Okay, so now it's time to quickly look at the attacker and threat model, just to contextualize our findings. DDS is a local system, is situated deep in the control network, and I would not expect to find any exposed DDS node. We checked, we scanned, we mass scanned the IP space for a few times, but we haven't found any exposed DDS nodes. Maybe with the in the future, we will see more and more ROS2 implementations. Some of them may go public for design or for mistakes. So we might find some DDS exposed nodes in the future. But I would say that DDS, from an attacker standpoint, DDS is more for local attack opportunities, such as discovery of other endpoints or lateral movements, and why not, from a malware writer standpoint, could be a good protocol to implement a CNC system. Speaking about remotely exposed systems, it might be the case that in the future we will see integration services being exposed. Integration services are an add-on component of DDS, is not a standardized part that most of the vendors offer to bridge several DDS systems together that are remote or in different network segments. I would say that it would be good to see in the future more agreement among vendors about using integration services, and maybe why not some standardization efforts. because that's the way, the proper way to integrate different DDS systems. And we have seen, on the other hand, that when these services are not part of the DDS implementation, system integrators tend to use custom-made solutions, which do not offer the same guarantees of an integration service, which allows control of who is talking, who can talk to whom, and how. To conclude, I would like to mention a few words about mitigation and disclosure. When we're talking about critical software components such as DDS, talking about mitigation is already too late, because most of the times we cannot simply patch. We don't even know where the systems are, because it's a library that is going to be incorporated into many systems. So if I get asked what about mitigation, I usually say it's too late. Well, mitigation starts with a good disclosure in these cases. So that's why we decided to start a little bit differently this time with this project. Instead of notifying the vendors only when we had findings, we have started to find contacts with vendors before starting to find vulnerabilities. We wanted to find, to establish a good relationship and so on. So the question is this transparency paid back or not? In some cases, it worked very well, I would say, and that's the case of AD-Link, which is now on stage with us giving this talk, which even helped us to write some fuzzing harnesses and to improve existing fuzzing harnesses. So I would say big round of applause to AD-Link. And what didn't work well, you saw that vendor that has never responded, not even to 5 times, consecutive times, trying to find a contact. This shouldn't happen for critical software, I would say. So the question that I leave here for the audience is, should we be treating vendors less like black boxes during the disclosure process and make the process more cooperative instead of just a coordination process that triggers, that starts when there are some discoveries? For future work and conclusions, I would like to say that we just scratched the surface because DDS implementations are many. There are 6 certified ones, but there might be more non-certified ones. The code base is large. The smallest code base still take minutes to compile. So it's a complex system. We need more researchers to look into. And we need implementers to be more cooperative. So don't be afraid and just reach out. As for future work, there is lots of other targets that we haven't looked at. We decided to focus on the core. To start with, there are X types, which is the type extension system. There is DDS security. There is integration services that I quickly mentioned earlier. Those need security experts to look at. So to conclude, as any traditional Black presentation, it has to conclude with sound bites. The Data Distribution Service, or DDS, is a crucial protocol for the connected world, I would say. I know it's a buzzword, but it's more prevalent than we know. We discovered vulnerabilities in most of the implementations, and some of the vulnerabilities were even affecting the specification. So we are working on that to get it fixed at the spec level. And as part of this presentation, we release an open source layer to parse and parse and forge DDS and RTPS packets as part of SCAPI. And we also released the fuzzing harnesses that we are currently integrating into the Google OSS Fuzz initiative. So we encourage other researchers to do the same. Thank you very much for following, and let's open the floor for questions now.